You're listening to The Solution, a podcast by Growers Mineral. I'm your host, Russell Bobel. In this ongoing series, we will be taking a look at the book More Food from Soil Science, a book written in 1965 by one of Growers' co-founders, Dr. V.A. Tietjens. In today's episode, we listen to the second part of Chapter 2, titled, The Reason for the Many Effects of Limestone Have Not Been Well Understood.
Greenhouse roses respond to heavy calcium feeding. Much can be learned by growers from experiments to determine their own particular soil needs for calcium or magnesium. A greenhouse rose grower has considerable trouble getting a type of growth that was conducive to a high yield of good quality roses. He asked me to examine the plants and diagnose the trouble. He had been a student of mine and had been reluctant to call me in, but he said, "I have been trying to figure it out with the principles which you taught me, but it seems I can't make them fit together, so they do me any good." I told him, if we can set up sand culture experiments on the basis of those principles and reproduce certain plant responses time after time, they must be sound. If you can't do that on this soil, it means there is something about the soil you haven't found out. "I may have slipped up on my reasoning," he said. "Well, let's have a look and see what is wrong with your plants." The plants appear to have too little calcium, so I naturally inquired, what is the pH of the soil? "Practically neutral." "Have you tested for calcium?" "No, but I have used calcium nitrate on this bed, and it is no different from the others." This was a little disconcerting because calcium nitrate will correct a low calcium condition. I took my test kit and microscope to his greenhouse and went to work. The plants were soft and watery with very little substance to them. The leaves were small and had a sickly yellow appearance. I tested for all the things I had equipment for and decided that the symptoms were truly those associated with insufficient calcium. So I asked, "Are you sure those solutions you have for your tester are all right?" He didn't know, so I took a sample of soil from several beds, had the available calcium determined, and found the test to show a trace of calcium, low to medium magnesium and phosphoric acid, and high potassium and nitrogen, a typical proportion of plant nutrient materials which, if used in a sand culture, would produce the type of growth found on those roses. What was needed was more calcium, so an application of 2 tons of dolomitic ground limestone was made over all the beds. Then 5 plots were selected, each 50 square feet, and an additional ton of limestone per acre was applied as a check against over-liming. This lime was applied in the middle of August. The prospects of a Christmas crop were poor. 20,000 roses were a liberal estimate. 4 weeks later to the day, Frank hailed me on the street and said, "I wish you could see those roses. You wouldn't know the place." "How were the plots that had the extra ton of limestone?" I asked. "You know, it's a funny thing, but those plants are growing faster than the others. I gave orders to have another ton of limestone worked in between the plants." "What are you using for fertilizer?" "Tankage and horse manure for mulch." I saw the roses several weeks later, and I could hardly believe I was in the same house. The plants had made 4 to 6 inches of new growth. The leaves were large and had that rosy green cast that growers like to see on growing plants. I noticed particularly that breaks were evident at the axils of the leaves as well as on the lower part of the stems where those large heavy canes originate. Had it not been for those plots scattered through the house, the grower would not have used more than 2 tons of limestone. Because these high lime plots continued to grow faster than the others, half-ton applications of ground limestone were made until the houses had received 7 tons of limestone during a year's time. The first Christmas harvest was 39,000 roses instead of the anticipated 20,000. A year later, it was 105,000. And since that time, he had an exceptional yield, which has been continuous regardless of crops pinched for holiday seasons. The important observation made here was that even though 5 tons of limestone had been added to a soil which was only 6 inches deep in beds underlaid with cinders, the pH remained about 6.6. This soil is considered a heavy sandy loam of the sassafras series, containing considerable organic matter. A quick soil test a year after the first application of lime was made showed a reading of very high calcium and high nitrate nitrogen, low to medium phosphoric acid, and high potash and magnesium. The tankage and manure used as a mulch supplied ammonium nitrogen, which could be readily absorbed by the roots because of the near neutral pH and abundant calcium, or could be oxidized to nitric acid, which, when neutralized by the limestone, was taken in as nitrate nitrogen. These changes, the formation of acids, undoubtedly prevented any tying up of iron, manganese, and boron, which sometimes is associated with too much hydrated lime in the soil. It did demonstrate the need for applying sufficient limestone to supply the lime requirements on a soil in which heavy mulches are continually maintaining a high level of chemically active organic matter. One of the dangers of too much lime supposedly is that it ties up the minor elements in the soil so that they are unavailable to the plant. This occurs with burned lime, but is not very much with pulverized limestone. The difference in solubility of the two forms of lime is responsible. I have yet to find a case of over-timing injury where a grower has used limestone and some form of ammonia as his source of nitrogen. In almost all cases that have come to my attention when stunting of the plants or definite injury occurs following a heavy application of burned lime, nitrate has been used as a source of nitrogen. There is considerable experimental evidence to show that nitrate nitrogen is most efficiently used by plants at a low pH of 4, while ammonium nitrogen is most efficiently used if the growing medium has a near neutral pH. Furthermore, if plants are supplied with only nitrate nitrogen at near neutral pH, chlorosis due to iron deficiency may develop and may be difficult to correct. Using ammonium nitrogen at these same pH values very seldom gives any indication of iron deficiency. In a soil, ammonium nitrogen does not remain as much for any appreciable period, so that plants probably only absorb a small percentage of that released in the soil, a very small percentage. The formation of nitric acid and subsequent nitrates undoubtedly helps to maintain some available minor elements for the growing plants. Potash deficiency may occur where too much burned lime has been used due to the fact that the plants must take in too much calcium for the potash they can get. Experimental results show that some plants grow best when the solution contains 5 to 7 parts of available calcium to 1 part of potassium. These relationships between nutrient materials in the soil are extremely important to the welfare of the plant, and calcium plays a major role in these relationships. Asparagus is a heavy feeder on calcium. Crops vary in their calcium needs. Asparagus requires large quantities of calcium. It actually uses more calcium in its growth than it does nitrogen, phosphorus, or potash. Yet most growers try to grow asparagus without lime. The results is inevitable. Average asparagus yields the country over vary from 80 to 110 crates per acre. Growers who make a practice of keeping the available calcium reading in the soil high or very high are harvesting up to 3 times that yield. 2 neighbors had an argument as to whether asparagus needed lime. One grower argued that there was enough calcium in their soils, but the others disagreed. Each went his way. I saw the acre yields of these 2 growers covering 3 years of harvest. The yields on the limed farm kept increasing each year. The grower, who did not keep his calcium reading high, had the opposite result. His yields were gradually decreasing. The highest yielding bed of asparagus I have ever seen, 350 to 400 crates per acre, had been given 2 tons of dolomitic ground limestone every year for 6 years. The pH was neutral, Every year, this grower also used manure and mixed fertilizer containing nitrogen from sulfate of ammonia. There were plenty of growers in this area who were using the same amount of fertilizer without lime, and their yields were only average. Growers should experiment with an acre or even a smaller plot to find out whether lime will give a response. This is as true for all crops as it is for asparagus. It is impossible for any experiment station worker always to make a recommendation that will cover all cases because he does not know what has gone on before. He can, however, advise the grower about certain trials that might be made to determine what will prove to be good practice for his soil. The question may be asked, why put on lime to correct acidity and then add a fertilizer that will make it acid? That question has been asked by many growers. The answer is the result of experience. See the discussion that follows. I set up what I considered an ideal experiment a number of years ago on Cape Cod. It involved 6 acres of 40th-acre plots, each plot replicated 6 times. The crop was asparagus. The soil was beach sand, which at the time had only a few brambles growing on it. We had fertilizer quantities up to 1,200 pounds per acre on different plots. Arthur Brenner, the cooperator, was a good grower, and I found him an excellent cooperator. We prepared our plots and set in 1-year asparagus roots on June 1st. We were very careful to have them all of uniform size. The asparagus started to grow uniformly. Less than 1% of the roots failed to grow. The last week in August, Arthur called to tell me that something peculiar was happening. We examined the field and noticed that the asparagus on the north half of the field was 2 feet tall and well-branched, while the asparagus on the south half had only 6 to 8 inches of growth. The first thing that I thought of was residual fertilizer. When I asked Arthur about that, he informed me that the land had not been farmed for 3 years. Before that, carrots had been grown on the north half and turnips on the south half. The weeds had been so bad in the carrots that they were plowed under, while the turnip crop was kept clean and harvested. When we checked the plot treatments, there was no difference on either half of the field. The soil test showed nothing. The second year, the plants on the south half looked almost as good in late summer as those on the north half after a season's growth. But the fertilizer treatments did not produce any difference in volume of growth that year. I never did hear what happened to these plots in later years because I left the Massachusetts experiment station before I could make further observations. In another experiment that I set up in Massachusetts, I picked a piece of ground between 2 stone fences. This land had been cultivated for many years. It was a good silt loam with a high organic content, the result of having manure applied with wood shavings for many years. The field was plotted with various amounts of fertilizer and plant with uniformly large asparagus roots. By the end of the first year, I had another failure. The plants along the edges were 3 feet tall, but toward the center of the field, they became successively shorter. In the center of the field, they were only 1 foot tall. The surface of the field did not indicate any irregularities. We dug holes, beginning at the center of each field, every 10 feet working toward the outside. The surface soil, 8 inches deep in the center, gradually increased to 24 inches deep on the margins along the stone fences. We discovered a well-developed plow soil which the roots could not penetrate. The subsoil of this field was low in available calcium. Apparently, the organic matter in the surface soil and the depth of the soil counteracted the magnitude of the deficiency of calcium in the subsoil on the growth of the experiment. The soil composition and amount of topsoil proved more important than the fertilizer that we had applied. I mentioned these things because most people have the idea that to grow a crop, all you have to do is find out how much fertilizer is needed for good yield, apply the fertilizer, and reap the harvest. Usually the result is a 35 to 65 bushel yield. Actually, after 25 years of research and observation, I am of the opinion that chemical fertilizers play a minor role in our yields, even though tremendous amounts of fertilizer are required. The fact is, often the major cost of growing the crop is the cost of fertilizer. If one puts sufficient thought on the problem, one soon realizes that there are yield-controlling factors which are far more important than fertilizer. Many of the ideas that we accept as proof of the pro-fertilizer philosophy are merely much-repeated idle comments made in the early days of the industry, which we would find difficult, if not impossible, to prove today. I was called in on an asparagus problem in eastern Maryland. This gives some idea how much limestone may sometimes be needed. A fertilizer company was being blamed by a grower on a farm on the eastern shore of Maryland for a low yield and poor quality of asparagus. I value this grower's friendship, so I will not give his name. He had had the reputation of supplying a commission merchant on the New York market with top-quality asparagus. They put up a banner across their booth announcing when his asparagus was available. In most recent years, he had lost the name. He blamed his fertilizer company for his troubles, since they had advised him to switch to a neutral fertilizer to avoid applying lime. He was a Cornell graduate and amused himself by reading science, soil science, and other scientific journals. He had called in specialists from several experiment stations and had received a different explanation from each as to the cause of the trouble. A representative from his fertilizer company called me in for advice. I immediately recognized his problem as calcium deficiency. This was met by a derisive laugh on his part. He had tested the soil and the pH was okay. It was a little above neutral. I told him it might still be calcium deficiency and that there was only one way to find out: lay out some lime plots to see what happened. This he agreed to do. He took 2 rows of asparagus across the field and applied 1 ton of limestone per acre. On the next 2, he applied 2 tons. On the 3rd pair, 3 tons. On the 4th pair, 4 tons. And on the 5th pair, 5 tons of limestone per acre. This was done at the end of the cutting season around the middle of July. Late that fall, I was invited to inspect these plots. I had an approximate idea where the plots were, and as I drove along his lane, which was beside his asparagus field, I was surprised to see 2 rows of asparagus that had made at least twice as much growth as any others. Since there were 10 rows in the experiment and only 2 showed any improvement over the rest of the field, I did not associate the good growth with the limestone treatments. When we arrived at the house, the grower asked me whether I had seen the experiment. I said no, but that I noticed 2 rows of asparagus far above the others. That is the experiment, he said. I asked him which treatment showed up. He said it was 5 tons. When I asked him what he was going to do now, he answered, I have ordered 250 tons of pulverized limestone to put on the field. As soon as I find I can get it, I will start hauling. That means over 40 trips to the quarry in Pennsylvania. 2 years later, he stopped in to see me on a return trip from the New York market. Well, I topped the market with my asparagus again this year, he said. It was some 8 years later, after I had moved to Virginia, that he had stopped by to see me on his way home from Florida. He had spent some months recuperating from some sickness and did not mention asparagus. I asked him whether he was still in the asparagus business. He pointed out the window and asked me how I supposed he had bought that new Cadillac, who was paying for the sojourn to Florida. Are you still topping the market? I inquired. Never missed, he answered. The secret of growing asparagus is to pile on the limestone. I am putting some on every year. Do you think you need it? I asked. I don't know, but I'm not taking any chances. It costs money to gamble. There is a general feeling among horticulturalists that, from a fertility standpoint, asparagus is a hard crop to work with. Results are often confusing. The difficulty seems to be in the starting point. None can be gained from fertility studies if calcium deficiency is the limiting factor. I wasted a lot of time conducting fertilizer experiments on asparagus until I discovered that asparagus is a lime-loving plant needing a large amount of available calcium because of rapid root growth. Physical and chemical soil conditions, therefore, were controlling factors in its growth. When there was sufficient calcium available, fertilizer treatment showed growth differences which might result in increased yields. During my teaching days at Rutgers University, I had the pleasure of presenting to a group of short course students a practical course on plant nutrition. One day during my discussion on lime, I made the statement that a pH test did not necessarily tell the lime needs of the soil, particularly for asparagus. After the lecture, one of the students stopped and said, "Did I understand you to say that a pH test was not enough to determine the lime needed in soil?" "That seems true from my experience," I answered him. After considerable discussion, he told me his father owned 100 acres of asparagus. They had tested the soil for acidity, and it always tested neutral, so they had never bothered to apply any lime. And if asparagus needed a lot of lime, he wondered whether this yield might not be low because of that. Since he had learned how to run a soil test in his laboratory exercises, I suggested that he bring some samples from the asparagus field and test them for calcium. It would be good experience for him. He brought 20 samples, tested them, and got no test for available calcium. He couldn't understand it. He brought his father along one Friday morning, and we discussed their problem. I suggested that they start applying 1 ton of pulverized limestone each year until their yields reached a higher level. His father had difficulty agreeing with my ideas, but since they had tried everything else while acre yields continually fell to lower levels, he figured he would not lose anything. I told him not to apply any fertilizer until he could see an increase in an acre strip on their field, where he continued to apply the lime. I also told him that he must believe in me because it might take several years before the limestone really began to show results in larger yields. They applied a ton of magnesium limestone every year for 7 years. I had heard nothing from him about his asparagus project until he walked into my office 5 years later with 10 tin cans full of soil. I asked him whether he had troubles. He said, "No, but I wanted to check the soil and talk with you." After he told me the following story, I asked him whether I could repeat it. He said, "Do anything you want, since it is really your story." My dad had grown asparagus for many years and had always been able to pay the bills, but during the 5 years, yields were getting lower each year. When I came to take the short course, Father was in debt to the tune of $9,000. We had to do something different or stop growing asparagus. When we found out what we should do to increase our yields, we followed your liming program faithfully. The second year after the first limestone application was made, our yield was slightly better, and we felt we might be on the right track. The yield was increasing each year up to the present time. During the past 5 years, many things have happened. I married my high school girlfriend, and my father built me a nice home. We have increased our plantings to 200 acres, and this year, after paying our bills and feeding 2 families, we had a balance of $7,000 in the bank. He gave me some figures on their average acre yields, but all I remember about them is the general trend. This soil was a sassafras Collingston fine sandy loam. Ordinarily, it should not require more than 2 tons of limestone per acre. But as the plants grow, they build up organic matter from the decay of the voluminous older roots. This undoubtedly increases the calcium requirement. Also, these soils are acid throughout the depth of the profile, each acre-foot layer requiring as much limestone as the surface layer. Over the years, the lower level in the profile becomes calcium saturated, permitting deeper rooting and increasing the calcium requirement even more. I don't suppose the time would come when this grower could feel sure that his soil was completely saturated with calcium, that he had applied sufficient limestone to grow his biggest possible yield. Theoretically, he should have reached a saturation point by 1945 on this soil type, but he apparently was benefiting by additional limestone applications. When he once reaches the saturation point, the yield should level off and continue to maintain that level for 10 or more years before it becomes necessary to apply additional limestone. Calcium serves many functions for the plant. If all the functions of calcium in the welfare of plants were enumerated, It would be necessary to start with the effects on soil and mention, among many others, such factors as overcoming baking of the soil when dry. Limestone improves aeration and drainage and tends to make soils granular. It prevents certain soils from becoming slippery when wet. I was very much impressed when, while I was a student studying soils, the instructor asked us to take 2 lots of soil and add a pinch of hydrated lime to one and a pinch of soda ash to the other. The 2 lots were then moistened, packed into balls, and placed on the edge of the furnace to dry. The next class period, the 2 balls were examined. The one with lime crumbled up very easily. The one with soda ash was as hard as a brick and could not be pulverized with the fingers. I believe the soil was picked especially for this purpose, because not all soils would be suitable for such a demonstration. Yet one has to only visit farms to view similar demonstrations on many of them. They say, "I can't get my beet seed up. Guess I will have to plant radish seed again. Can't get my seed planted until we get some rain." Those are calcium problems, pure and simple. They may not be easy to correct. I have in mind an experiment in which a given lot of beet seed was planted on 9 lots of soil taken from as many farms, all having different levels of calcium and potassium. The germination on these lots varied from 10% on the soil having the lowest available calcium to 100% on the one having a high reading of available calcium. Then there is the factor of supplying the calcium needs to the plant. Too many people still consider calcium a soil tonic and not as a plant food material. They still think of calcium as being a corrector of acidity and determine the calcium levels by the pH test. Plants are still better indicators of the available calcium level than laboratory apparatus, and if the responses of plants do not seem to fit with our theories, perhaps we had better overhaul our theories. Calcium, when once taken into the roots of the plants, goes to work. If there are acids present, it ties up with these. Plants like tomato, spinach, and asparagus, which have oxalic acid form in the protoplasm, contain calcium oxalate crystals, which can be seen with a microscope. Were it not for this function of calcium, these acids would soon kill the plants. Then, too, calcium has an effect on the proteins of the plant cell, keeping them more or less stabilized. It tends to keep the proteins properly suspended in the cell sap, while potassium, sodium, and ammonium tend to keep them highly watered or hydrated. This is probably one of the reasons why it is necessary to maintain a certain balance between calcium and other nutrient materials. Protoplasm with too much calcium or too much potash probably would not support our plant processes very efficiently. Too much calcium tends to dry out or harden plants. Too much potassium tends to soften them excessively. This is probably an indication of why fertilizers carrying 20 to 30% potassium are needed on soils having available calcium, especially for those plants which have a high potash requirement. This is difficult to understand and to prove because under variable weather conditions, it is difficult to get an accurate reading of the potassium content. Calcium also combines with pectic acid to form the cementing material which holds the cells together. None of the other materials which are absorbed by plants could function in this capacity because they would not form insoluble compounds. Calcium must be continuously available because plants must have a steady supply. It does not move around very much in the plant. When all the functions of calcium are grouped together, the end result is the manufacture of protein and sugar in the plant and food for humanity. Experiments show that if calcium is not present in sufficient quantity, these processes are interfered with and the amount of sugar, starch, and protein formed is materially reduced. Because of the importance of calcium in human diets, the amount of calcium which can be taken into the plant and stored involves a major consideration. It is possible to produce plant food products that have a minimum amount of calcium on soils that are too low in available calcium. Such crops are not profitable for the grower, nor do they satisfy the requirements of a good food. There is a general opinion that horses raised on Kentucky bluegrass are well nurtured. Kentucky bluegrass is a high calcium grass. Perhaps there is a thought worthy of serious consideration. I saw a carload of 300-pound Hereford steers unloaded in eastern Virginia and placed on a well-limed pasture. 7 of those steers were placed on unlimed pasture, but lots had plenty of feed and water. 3 months later, I saw those same steers. Those on the limed soil were fat and slick. Those on the unlimed pasture had grown larger, but looked as rough and scrawny as the day they were put on the pasture. My friend in Elgin called it white gold. I wonder whether even that signifies the value of the millions of tons of limestone available for better food plants for human and animal consumption. The importance of calcium for large yields. To talk intelligently about soil fertility and crop yields, we must understand about soil and plant colloids and base exchange phenomena. Nutrient ions necessary for plant growth must be in solution so that they can be absorbed into the roots. Soil and plant colloids help to store these nutrients in the soil and in the plant. They make possible the base exchange phenomena, which makes it possible to apply large quantities of lime and fertilizer to a soil, which can then hold it in readiness for the plant when it needs it. When we apply limestone and mix it with the soil, we have a mixture which is only partially ready to support a good crop. Not until the calcium and magnesium in the limestone have disintegrated and become part of the colloidal complex in the soil through base exchange reaction does the growing crop benefit from the calcium and magnesium in the limestone. If limestone is applied to the soil and the ground remains dry, the limestone remains ineffective. If the limestone is too coarse, it may not be effective very rapidly. Good plants and crops can be grown in pure sand. A sand culture is nothing more than coarse sand, to which a weak nutrient solution is added. The plants are actually growing in damp sand, but it is necessary to apply nutrients every day because there is no colloidal material to prevent the salts from burning the roots or building up a high specific gravity. As soon as a little chemically active colloidal material in the form of a very fine clay or organic material like milk casein is added, we no longer have a sand culture. We have the beginning of a loamy sand, which can soon become a sandy and even a silt or clay loam. This adds complications to our culture. We have introduced materials which make soil acidity and base exchange phenomena our controlling factors. It is necessary that we know the nature of these colloids. Colloids in the soil are both mineral and organic. Mineral colloids consist of mixtures of iron and aluminum oxides with silicon dioxide, which remain stable above a pH of 4.7. They may be a continuous jelly-like film, or they may be large structural molecules. Organic colloids consist of carbon compounds, usually combinations of proteins and amino acids, in combination with humic acids, the last stable products in the decomposition of organic matter. They, too, may exist as jelly-like films or as particles of large, complex molecules. The important thing is that these colloids are surrounded by millions of negative ions or charges, which in the natural state are in balance with hydrogen, a positive ion. Hydrogen is a very weak ion and is readily replaced by any other basic ion, such as calcium, magnesium, potassium, sodium, and ammonium. The number of hydrogen ions so attached in a given volume of soil, along with those existing as free acids or alkalis in the soil, determines the pH of the soil. In order to be able to give a usable figure, we use the logarithm of the total number of hydrogen or alkaline ions. A soil with a pH 4.7 has millions of hydrogen ions or charges. This soil would be very highly unsaturated. Any of the basic materials could be applied to saturate the soil. Soda ash could be applied in sufficient quantity to sweeten it, and the soil would be sodium saturated. It would have a pH of 7.0, but would not grow a crop. Such a soil, if kept dry, would make good bricks. We have formed such soils in the past by the use of excessive amounts of nitrate of soda on sandy loam soils. The same thing could be done with anhydrous ammonia, caustic potash, or the oxides of the other basic ions. However, the only one that could be used if good crops are to be grown would be calcium, such as in some of our early limestone soils. Scientists who have studied this problem say that at least 85% of the basic material needed on a given soil must be saturated with calcium. For some reason, the calcium ion, of which we have unlimited quantities stored on this earth, has properties that are especially suited to support life, whether it is plant or animal life. Since there is such a preponderance of calcium, we might assume that all life evolved on this earth adapted its functions to calcium rather than to other minerals. Thomas J. Way, an English scientist who worked in the early 1850s, R. Gans, a German scientist in 1905, D. J. Hissink, a Dutch scientist in the 1920s, and K. K. Gedrois, a Russian scientist in the 1920s, are responsible for our fundamental information on the theory of why calcium is important in soils and why different soils need different amounts of calcium to make available to the growing plants the calcium that it needs to ensure maximum yield under varying weather conditions. Since the stage was set on which to build a profitable crop program, such men as Wheeler, Bert Hartwell, E. Truog, Sante Matson, Jacob Jaffe, W. P. Kelly, Hans Jenny, Michael Peach, Marshall, and others have contributed to our understanding of how this calcium ion functions in the soil. As a result of my graduate studies with Dr. Sante Matson, I feel very strongly that there is a parallelism between the relation of calcium to the colloids in the soil and the relation of calcium to the colloids in the growing plants. Plants which have their colloids saturated with calcium apparently make better food for animals. The process of substituting calcium through the application of limestone to replace the hydrogen on the soil colloids is referred to as base exchange. The base exchange complex in connection with the soil colloids is responsible for all our fertilizer problems. The greater the quantity of base exchange material that exists in the soil, the more complex the soil becomes. The application of nitrate of soda, muriate of potash, a common fertilizer ingredient, has been involved in our fertilizer experiments because it has so many possible effects. I witnessed an experiment in which numerous plots were treated with various amounts of limestone from 400 pounds to 6 tons in increments of 800 pounds. Then, 1/2 of each of the plots was given 300 pounds of muriate of potash. Alfalfa was grown on the plots. The potash doubled the yield on the low-limed plots, but the total yield was less than a ton per acre. The intermediate limed plots did not show as much increase attributable to the potash, and where heavy limestone was applied, there was no increase in favor of the potash, even though the total yield was 6 tons of hay. In other words, calcium was the controlling factor, and the value of the potash in the low-limed plots was to kick out of the base exchange complex the calcium which the alfalfa needed and absorbed from the solution. The application of calcium-carrying materials saturates the base exchange complex of the soil and becomes the keystone to efficient crop production. In it lies the secret of our future food supply. Base exchange of the soil means nothing to the farmer, and yet everything he does to his soil affects it. Even though colloids are a very minute part of the soil, they control crops more than anything else. If we talk about the pH of the soil, we are primarily concerned with the ratio of negative and positive charges on the chemically active colloids in the soil. If the charges are equal in number, we have a neutral soil in the true sense, but practically, the pH test may be below or above the neutral point. The minus and plus charges may not be the same strength, which would influence the pH test toward the acid or alkaline side. The most minute part of a dry soil is the colloidal matter. Milk is a good example of a colloidal solution. The curd in fresh milk is a colloid, and as long as it is sweet, the curd remains suspended in water. When milk sours, the colloids or casein settles out. It is a protein colloid, and it has negative and positive charges on it. Organic matter in the soil oxidizes and ferments to release proteins and amino acids, along with other products and actual acids from fibrous and starchy material liberated from the organic complex. These all mix with the mineral to form a very complex compound, which in some cases actually combines to form a complex mineral protein taking on millions of negative charges. The decomposition of organic matter, crop refuse, and manure results in finely divided molecular compounds, often referred to as the humus in the soil. When it is dry, it is a very fine dust. When wet, it may become a colloidal solution in water. If we were to take all the ammonium, potassium, sodium, calcium, magnesium, manganese, and other basic elements out of the soil, we would have a 100% unsaturated base exchange compound surrounding the fine sand particles, and the pH in a temperate climate would be close to 4.7 if it was all mineral, or 6.8 in southern soils. If it had a lot of protein mixed with it, it could have a lower or higher pH when completely unsaturated. When the base exchange complex is unsaturated, it is not possible to grow a crop on the soil. Too much iron and aluminum would come into solution, making them available to the plants by making them soluble in water, and, since they are toxic, they would poison the plants. That is why limestone is applied. The limestone must be very finely ground so that it will come into contact with as many soil particles or molecules of base exchange substance as possible. That brings about quick interaction with the limestone. The calcium and magnesium from the limestone exchange partners with the hydrogen on the soil colloid, making a new compound, a calcium-saturated base exchange complex, having a neutral pH, practically 85% saturated with calcium. If there is some magnesium, then the magnesium accounts for some of the saturation in place of the hydrogen, but for the best yields, it should not be over 10% at the most. A very high magnesium limestone will cause more magnesium to be held on the colloid. This complete saturation immediately starts oxidation in the soil, and the minerals begin to disintegrate to release potassium, phosphorus, manganese, and other elements. Some of these then exchange places with the hydrogen or even calcium on the colloids and, through the base exchange phenomena, make calcium available. Thus, calcium comes into the soil solution, along with the mineral constituents needed to make up a balanced nutrient solution. If practically all the hydrogen is replaced with calcium, we have changed a worthless soil to a highly fertile, productive one without applying fertilizer. The displaced hydrogen has joined with the carbonates to form a carbon dioxide water mixture. The carbon dioxide may then be released into the air, or it may work on the limestone or other minerals as a very weak acid to carry on the weathering process, which releases plant nutrients. Water, sunshine, and temperature can make such a soil produce large crops. When certain types of dry fertilizer or fertilizer solutions are applied to unsaturated soils, absorption of the basic elements into the colloids prevents plants from absorbing them, and nutrient deficiencies occur. Acidic ions or negative ions such as chlorides, sulfates, nitrites, and phosphates are left in the soil solution, but since they outnumber the basic materials, we find a solution badly out of balance. Some plants can make some growth in such soils, but it might be possible to grow 20 bushels of corn, 5 to 7 bushels of soybeans, 10 bushels of wheat, 75 bushels of potatoes. But when we apply 5 to 20 tons of limestone on such a soil and mix it in, it immediately boosts those yields 4 to 5 times because the soil solution has been brought into a balance better for crop production. This improved balance also means that we have improved the environment for bacteria. so that more nitrogen is manufactured from organic matter. We have speeded up chemical processes so that oxidation of minerals is speeded up. This releases potash and phosphorus along with other elements needed by plants. If soils are adequately limed, nothing should be wrong with them except possible element deficiencies needed for specific growing crops. But there are other things that affect soils which can prevent us from growing high crop yields. They are all indirectly associated with partially unsaturated soil colloids. According to physical-chemical laws, there is a water-ion relationship which affects soil and crops. Each ion has an affinity for a certain number of ions or molecules of water. Calcium has a small number, potassium has more, sodium still more, and lithium still more. Others fall somewhere in between. Colloidal clays and protein will swell up in varying degrees depending on the ions hooked into them. A calcium-saturated clay has a low degree of swelling because calcium has only 3 molecules of water. The same amount of clay saturated with potassium will swell more because it has 5 molecules of water. Sodium clay swells still more because it has 7 molecules of water. Such soils, when dry, will crack, an automatic aid to air penetration and some oxidation. Drying out a soil has a temporary mellowing effect, just as freezing does. The effect of fall plowing helps to mellow cloddy soils because it helps to freeze those soils. Salt marshes have extremely wide cracks when they dry out because the colloidal material is so heavily saturated with sodium or hydrogen. They also bake very hard. Brick manufacturers have found that the hardest bricks can be made by mixing soda ash with the clay. A clay saturated with calcium makes soft bricks and will crumble. Thus, a clay soil heavily limed becomes crumbly and won't become hard when it dries. The same quality in the soil affects the quality of the crops. The same chemical reactions exist between proteins and ions in the tissue of the plant, as well as between the soil colloids and the ions in the soil solution. Thus, corn will grow on a soil well saturated with calcium when the plants can absorb calcium freely. The calcium is held in the cells by the proteins, and a high proportion of proteins to amino acids is present. The maximum amount of dry matter per 100 grams of plant tissue is produced when adequate calcium is present. If the plant can't get enough calcium, it absorbs more potassium, sodium, ammonium, magnesium, or other ions. These all have more molecules of water hooked to them than when calcium is present, so the plant growth becomes more lush and has dry matter per 100 grams of green material. Under these conditions, the ratio of storage proteins to amino acids is lower, and the feeding value of the crop is lower. This often happens when growers use too much nitrogen. Cattle feeders have told me that corn grown on well-limed soils will produce more beef or milk per pound of silage than corn grown on soil that does not have sufficient lime on it. It has also been shown that corn grown on well-limed soil will not get moldy and has less shrinkage in the crib than corn grown on inadequately limed soils. This is all associated with the bound water effect, or we may even say the colloidal base exchange phenomena which exist in the plant. Corn grown with too little calcium won't mature as quickly, is slow to dry out, and readily absorbs water in a damp environment after it has been dried to 15.5% moisture. From this, it may seem that soil and plant colloids control practically a farmer's fortunes. They have a direct bearing on his net profits, and the condition of these colloids with respect to calcium pretty much controls his health and that of his animals. Therefore, the proper saturation of the base exchange complex, whether it is in the soil or in the plant, is the keystone to crop production. The interacting forces established or existence at any given time in the quality of base exchange or buffer system, as many refer to it, determines how readily the plant can get its necessary plant food material out of the soil. Thus, it controls the yields of our agricultural crops. With good farming conditions, oxidation in the soil, and the adequate moisture, any cultivatable soil may grow 300 bushels of corn without supplying any appreciable amounts of fertilizer. Criticism against the use of dry fertilizer does not condemn it. It is a criticism against how it is used. Fertilizer cannot be used to grow crops when the plants are grown in pure white sand, because there is too little calcium present. In soils, calcium is just as important. Indeed, it is more important than fertilizer in setting the stage for big yields. Calcium comes in many forms. Liming materials include any calcium material that lowers acidity when applied to the soil. The following may be classed as liming materials. 1. Limestone carbonates, marble dust and chalk high in calcium, calcite high in calcium, dolomite contains a high proportion of magnesium, oyster shell high in calcium. The effectiveness of these depends on how finely they are ground. If they pass through a 100 mesh sieve, they are good for soil application. They may be coarsely ground, which makes them slowly available, or pulverized to make them almost as active as hydrated lime. 2. Burned lime oxides, very active. 3. Hydrated forms, hydrates, very active. 4. Special forms, shell marls, carbonates. Soft and low grades may be slow acting. Lake marls, carbonates. Gritty and slower acting. Slag, basic oxides, active. Slag, Thomas, calcium and magnesium silicates, moderately active. Wood ashes, active, oxides. Most important from the standpoint of soil fertility is whether they contain both calcium and magnesium. We must replace the hydrogen on the colloids with calcium and magnesium. This means attaching calcium ions and a few magnesium ions to the mineral and organic colloids. Limestone also neutralizes the acids formed by oxidation of organic materials, sulfur, phosphorus, ammonia, and other ions. To understand lime and its effect on the soil, we must appreciate what the soil consists of. A sandy loam soil contains rocks, pebbles, gravel, from coarse to fine, sand of varying degrees of fineness, much of it minerals, silt of varying degrees of fineness and mellowness, clay, some minerals, and some quartz of varying degrees of fineness, some of which is colloidal or chemically active, organic matter, roughage decomposed by bacteria to become fine enough to be colloidal. We are primarily interested in the clay, humus, and salts because their relative condition affects the growth of the plant. Much of the salt is usually in solution in a moist soil. Colloidal humus and clay are not soluble, but remain in suspension, just as the curd in milk stays in suspension, and are active chemically. They respond according to the laws of colloidal chemistry. If you place a handful of soil in a glass of water and stir it up, the last material to settle out is the colloidal material. It may stay in suspension for several days. Imagine clay and humus as being a series of shelves made of iron and aluminum, and the stuff on the shelves to be the ions such as calcium, magnesium, potassium, sodium, manganese, and so on. The shelves are deep, and the ions on the front may be obtained more readily by the roots than those on the back. Now imagine the root of a plant being a truck that backs up to the shelf to load up. It needs certain ions. If it gets what it needs freely, the plant grows normally. But suppose those shelves are loaded with potassium and nothing else. Then the plant doesn't get calcium and magnesium. It gets too much potassium and stops growing. But suppose the shelves are almost empty and only hydrogen ions are present. They are gaseous and the plants can't grow by taking in gas. In addition, the bench begins to deteriorate and the roots take in part of the shelf iron and aluminum. The root shrivels and dies. It is poisoned. In other words, we must keep those shelves strong enough and full of calcium, magnesium, and potassium in the right proportions. If the minerals in the soil don't supply those ions that keep those shelves filled, we must add them in the form of fertilizer. Calcium is the one most often lacking. We have to put on limestone to supply the calcium and magnesium. How does lime affect the physical condition of the soil? An acid soil low in calcium does not permit water to drain away. When it is wet, it becomes smeary. When it dries out, it becomes cloddy. A high pH may be brought about by sodium, potassium, or ammonium, whether there is calcium present or not. At a high pH, such a soil is slippery when wet and bakes hard when dry. The colloidal jelly holds too much water. A soil sweetened with lime is not smeary when wet, and it does not bake hard when dry. It holds only a small part of the water because the calcium ion does not attract water. A soil low in calcium dries out slowly. A soil high in calcium dries out quickly. Thus, a well-limed soil is much better aerated. A soil may be sweetened temporarily with certain fertilizer ingredients, such as sodium, potassium, or ammonium. In such cases, we get a phony pH which sweetens the soil but may cause certain deficiencies, such as calcium and magnesium deficiencies. According to published experimental data from research in England, Germany, Russia, and New York and Florida, it is necessary that a soil be limed to a pH equal to 85% of its calcium requirements to support best conditions for growth of crops. For instance, if a sandy soil has a calcium requirement equal to 1 ton of limestone in an acre-foot, it is necessary that 1,700 pounds of limestone be added to bring the top 7-inch layer into good condition. And to improve the soil down to a depth of 3 feet, we would have to use approximately 7,600 pounds of lime. The limestone that is necessary to bring up 85%, a clay loam having a calcium requirement of 4 tons of limestone in the upper 7 inches, can easily be figured. In an acid soil, it may be necessary to put 15 tons of limestone per acre to supply the necessary calcium to a 3-foot depth. Maximum growth may not be obtained unless this is done. The purpose of deep liming is to encourage deep rooting. When root growth is compared to a naturally acid limestone soil, the importance of a thorough liming program is realized. The following things happen when adequate limestone is applied. 1. Ready penetration of water by dehydrating the exchange complex. 2. Good aeration and oxidation. 3. Opportunity for up and down movement of water in the soil, resulting in better aeration and greater workability. 4. Extensive feeding area for the plants. 5. Opportunity for the roots to reach a water table in dry weather. Proper saturation of the soil complex with calcium controls yields. Saturation of the soil complex is so much Greek to most farmers. If you fill a 10-gallon pail full of sand, the space in the pail is saturated with sand. If lime water is added to the sand, it fills the space between the sand grains and the sand is saturated with lime water. If you add organic matter, acid, clay, and silt to the sand until the spaces are filled, you would have the sand saturated with organic matter, clay, and silt. Then, we would have something resembling an acid soil. The organic matter and colloidal clay still contain minute cavities which are lined with millions of negative charges, each one holding a hydrogen ion. We have a situation similar to a rundown battery, which is useless. The soil also is useless. If we make up a water solution of calcium chloride, magnesium chloride, and potassium chloride, it will be neutral. If we pour this solution over the soil and leave it for an hour, then drain the water off and test the soil, we will find it to be neutral. The calcium, magnesium, and potassium will have replaced the hydrogen ions, making the soil neutral. In the field, we do this by adding limestone and using the help of natural rainfall to wash the limestone into the soil. In other words, before we poured on this acid mixture, we had unsaturated or acid clay and organic matter. After we added the lime water, the soil became sweet because we saturated the clay and organic matter with calcium, potassium, and magnesium. There were still empty spaces where water and air could be held. Before we added the lime water, the sand probably would not have permitted seed to germinate, but with lime water, the seed germinated and supported the normal growth of the seedling. Like a well-charged battery, it is ready to go to work, just as a fertile soil is ready to grow crops. On soil that has not been farmed yet, we can determine the lime needed to saturate the organic matter and clay by determining the acidity. If we know how much active organic matter and how much clay we have in the particular soil, we can calculate how much limestone to add in order to saturate the soil complex. A sandy soil usually has very little organic matter or clay, therefore the amount of limestone needed would be low. As the clay and organic colloidal complex increases, the lime requirement increases. Thus, a clay-loam soil might require 10 tons of limestone, whereas a sandy soil might require only 1 ton for a change of pH from 5 to 6. Potassium, sodium, and ammonium salts can all influence the acidity test. They are more active than the calcium ion. If a soil is saturated with sodium, the pH might be neutral, but the soil would still need a heavy application of limestone because calcium saturation determines the growth of plants. A strongly acid soil has a great number of negative electrical charges, and the sum total of the charge or pull in the soil could be so great that positive ions such as calcium, magnesium, or potassium might actually be pulled out of the cells in the roots, thus preventing the plants from growing. Plant growers have noticed that plants growing freely in a good soil will be very slow to start growing when placed in a poor soil. I have been told that if you apply nutrient ions to the foliage of plants growing on poor soils, in a matter of minutes those ions may be traced through the stems and roots and out into the soil solution. We must think of this soil-plant relationship as one tending to set up a neutral balance between the base exchange mechanism in the soil and the isoelectric mechanism formed by the proteins in the plant cells. As long as we have equal numbers of negatively and positively charged particles, we have a neutral balance in which only an exchange between positive ions might take place, as would be the case if there were an abundance of calcium ions in the soil trading places with an abundance of potassium ions in the roots. In other words, there is a continual movement of ions back and forth until perfect equilibrium or balance is established. Since the new plant is growing and establishing more proteins with more new charges, the possibility of a true equilibrium cannot occur until all growth ceases and no more new charges can be formed. Thus, we can think of the growth of a plant as the result of ions being transferred from a saturated to an unsaturated condition. From this, we can see that the growing crop is to have enough of any one ion like calcium. The soil must first be heavily charged with calcium so that it will be readily available to be transferred to the waiting charge on the protein in the cell of the feeding root. The ease with which this equilibrium can be maintained could account for the many problems we see in fields where seed doesn't germinate or satisfactory growth of the seedling is not made if the seed does germinate. It is possible to grow plants in pure sand or in glass beads, but here we must maintain a nutrient level comparable to a solution having a pressure of less than 2 atmospheres, so that the necessary ions will move from water bathing the roots to the protein of the protoplasm of the root cells. This is far different from a soil having much chemically active clay and organic matter, including proteins, which are tenaciously holding the ions by a force of varying magnitudes. This force becomes weaker as the saturation point is reached. When it becomes weak enough to equal that force exerted by the protoplasm in the root cell, then an exchange of ions occurs, and the plant can increase in size as long as sufficient water is present to permit the ions to move. The rate of growth probably is correlated with the rate of movement from one charged nucleus to another. One of our better seed companies asked me to investigate a lima bean problem. A grower had bought enough seed to plant 40 acres, but when the seed would not germinate, he sued the seed company for having sold him poor seed. His soil was a loamy sand with a low base exchange capacity. The seed company had sold some of the same seed to another grower who had harvested a good crop. I took several bushels of soil from the plaintiff's field and some of the same seed that he had used to plant his field to my greenhouse, and I tested the soil. I found the pH reading near the neutral point, but the available calcium reading was less than 50 pounds per acre. The soil itself had an available calcium requirement of 2,800 pounds per acre foot. I filled several 8-inch pots with the soil. In several others, I mixed limestone with the soil, and in several others, I placed a mixture of gypsum in the pots with soil. I then planted a dozen seeds in each pot, wetted them down, and waited for germination. In 4 days, germination had started in the gypsum and limestone-treated soils. At the end of 2 weeks, 8 plants per pot in the gypsum-treated soil and 11 per pot in the limestone-treated soil had formed their true leaves. With no treatment, 4 of the seeds had started to germinate but had not gotten beyond the cotyledon stage. In other words, the soil received the calcium-supported quick seed germination, whereas the soil saturated with natural sodium instead of calcium would not support germination. I have always been much impressed by the work done by Gedroys in Germany many years ago. He conducted an experiment to determine the importance of saturating the soil with calcium instead of other positive ions. He took a soil and removed all the available calcium from it. 1/2 of the soil he divided into different lots and treated each lot differently with the various salts to replace the calcium. He planted seed and got no germination, except where he used a calcium salt. The other half was mixed with 2 tons of limestone per acre, and the different lot were treated as in the first lot. Again, only where he used the calcium salt did he get good germination. The limestone did not improve conditions for germination immediately. Then he set the pots aside for 6 months and again planted seed. This time, seed germinated in all the lots which had received limestone, but in the other series, only the one with the calcium salt permitted seed to germinate. The importance of calcium in arid alkaline soils was brought to my attention many years ago when I was consulted on a citrus orchard in Arizona. I had previously published a paper on the relation of the form of nitrogen utilized by plants and the pH of the soil in which the plants were growing. In other words, ammonia nitrogen was most effective in soils of low acidity, whereas the nitrate ion gave best results on soils of high acidity. This was in soils having available calcium. But when sulfate of ammonia was applied to Arizona's citrus trees, growing on the alkali soil, there was no response, and my theory was criticized. The foliage did not turn green, nor did nitrate of soda produce a response. First of all, his problem was calcium, not nitrogen, deficiency. At the high pH, the calcium in calcium carbonate was not available to the trees. Therefore, the calcium nitrate, and not nitrate of soda, would be an ideal source of nitrogen because of the increase from less than 100 parts per million to over 3,000. The trees all turned green, and what minor element deficiencies were present had disappeared. A combination of calcium nitrate and ammonium nitrate might have given an even quicker response. Lime and soil acidity. Calcium in the soil is like grease on an axle. It smooths out irregularities. One grower told me that the ease of plowing paid for the lime. During my college days, I had occasion to take many agricultural courses. I was disappointed in many of these courses. First of all, no attempt was made to inform the students that the courses were only the application of scientific facts to crop production. Secondly, many of the people giving these courses gave out information in a parrot-like procedure without regard to proven facts. I noticed that these courses were on no higher level than those taught to us in the county agricultural school. During the coursework, many platitudes were thrown out which meant nothing, covered up ignorance, and had not been and could not be proved. Some of these applied to the use of liming materials, things which I found I could discard without interfering with my accumulation of observations and facts on crop production. One of these was, "Lime makes the father rich and the son poor." I would change this to read, "Lime makes the father rich and the son a capitalist." The statement as it stands indicates that we know nothing about the action of limestone in the soil. It always seems to me that when we see the tremendous unlimited tonnage of various forms of limestone piled up in our backyards as a result of natural forces, and consider the importance of the calcium ion not only in our crop production practices but in the health and well-being of our animals and human beings, we, as scientifically trained people, are neglecting one of the greatest God-given gifts to humanity. The phrase overliming injury pops up every time any mention is made of the use of liming materials. It is a phrase that lingers on the lips of most people whose responsibility it is to hand out agricultural information. In itself, it means nothing, and therefore is a phrase of the uninformed. With multiple adjectives, it could mean something very definite. It is a phrase that was added to our literature when wood ashes and burned lime were used on the soil to correct soil acidity. Wood ashes have been used by plant-growing people since the 18th century. The story is told about the Mennonite scout who was sent out to look over a site for a settlement. When he inquired about an area adjacent to a river in one of the southern states, he was told the land was worn out. But he took a second look and found small round areas covering 5 to 10 square yards, where weeds grew in abundance. On examination, he found that these plants had deep roots, while those nearby were very shallow. As he studied these areas, he surmised that there were campfire sites of Indian tribes who had frequented the area many years before. Wood ashes and burned oyster shells had been left. He encouraged his people to buy this poor land and apply liming materials to grow their crops. Today, this is a highly productive community of farmers. I recall an interesting story published many years ago in Reader's Digest about a Reverend Mr. Orton, who was sent to the Smoky Mountains to take over a poor, run-down Methodist church. His first Sunday, he had fewer than 10 people to listen to his sermon. He decided something had to be done. These people were too poor to come to church. After a survey of his area, he decided he must show them how to raise enough food to at least fill their stomachs and in this way bring them to better health. Unlike his predecessors, who came to the church and left after the first sermon, he saw the light that would lead the community to better things. He bought a piece of land adjacent to the church. He applied adequate liming material to grow clover. He grew corn and other crops in abundance. The idea caught on and spread over a period of years following his experiment. Many farmers don't want to be shown. In a meeting that I addressed, a grower told me he had tried everything and he knew you could not grow 100 bushels of corn per acre. When I asked him if I could work with him and find out whether he could increase his yield, his answer was an emphatic no. I have conducted many field plots on farms where the increases were below the differences needed for experimental significance. Such plots don't help to solve farm problems. They do make you question your thinking. As a result, I have found that almost all soils need much more lime than a soil acidity test indicates. I have found that the reason limestone doesn't always show a response is because of such factors as inadequate mixing with the soil, prevailing moisture conditions, fineness of grinding, and kind of limestone all affect the speed with which the calcium saturation is accomplished. Unless a certain saturation point is reached, yields will not be increased. Lime controls physical condition of the soil. For many years, we have considered lime a corrector of soil acidity. The soil acidity tester was standardized for an acre-foot or 7 2/3 inches of soil. As long as commercial fertilizer was being used sparingly and barnyard manure was being used, problems concerning serious soil fertility deficiencies did not exist. There were carriers present in mixed fertilizers which could either acidify or sweeten the soil, but the quantities were so small that no serious problems resulted. Fertilizers with nitrogen from ammonia tended to build up more acid. Fertilizers with nitrate of soda or calcium cyanamide reduced the acid in the soil. Using both, one neutralized the other. However, the roots of crops explored the subsoil and removed calcium. Legumes, clover, and alfalfa feed heavily on calcium and magnesium. Removal of this calcium gradually tended to build up acid conditions in the soil by leaving acidic residue ions, unless there was enough residual limestone present and time was available to replenish the supply of available calcium. Limestone soils tended to maintain fertility over a longer period than the non-limestone soils, which had no residual limestone to draw on. Size of particles and solubility all contributed to the supply of available calcium. Thus, when we build up acid in the soil or remove calcium, particularly in the non-limestone soils, we must apply limestone in adequate amounts. 1 ton of limestone will add from 400 to 900 pounds of calcium, or the equivalent carbonate. Thus, for every 400 to 800 pounds of calcium needed in the soil, we must add a ton of limestone. If we need a ton in the surface, 7 2/3 inches, we may need an additional ton in the second layer and succeeding layers, particularly on the naturally acid soils. In order to speed up the effect of the limestone, it must be finely divided and thoroughly mixed with the soil and placed in the subsoil by means of deep plowing or the use of a subsoiler. The effectiveness of liming material depends on the fineness of grinding and the thoroughness with which it is mixed with the soil. The action comes about by contact with acid particles. Being only slightly soluble, the calcium can be absorbed by the acid particles on the soil colloids in the base exchange complex only slowly. If strong acids are present, the solubilization of the limestone is accelerated. Chlorides found in commercial fertilizers increase the need for liming material. When the chloride ion is released with muriate of potash, it must find something to attach itself to. Calcium seems to be a convenient companion, so calcium chloride is formed and, being very soluble, starts to move. If there is good drainage from the soil, the calcium chloride can be found in the drainage water in appreciable quantities. I have measured 40 ppm. This means that liming materials must be added to replace that which leaches away. For every 100 pounds of muriate of potash applied to the soil, 20 to 30 pounds of calcium is removed. A ton of muriate could conceivably remove the calcium from a ton of limestone. When sodium or potassium salts are applied to the soil, they are quickly dissolved in the soil solution and, being very active, they soon increase the calcium in the soil solution by replacement on the base exchange complex. Potash has been given the credit in many experiments for increasing yields, when actually the increased yields have been due to the increase in available calcium. Where a large supply of combined calcium exists, the application of other basic ions can stimulate growth. This is the reason why asparagus growers got good response to salt applications the first few years they applied it. When the calcium was depleted, salt no longer gave a stimulation. Many of the effects of nitrate of sodium could be attributed to the increase in available calcium rather than to a direct effect of the nitrogen. With ordinary mixed fertilizers, where a low-grade superphosphate was applied, approximately 1/2 of the superphosphate was gypsum or calcium sulfate. This calcium could offset the calcium lost with the chloride ions in drainage water. If, however, one of the high-analysis fertilizer mixtures, which are entirely soluble, is applied, the calcium problem becomes more critical since there is no calcium sulfate present and all calcium must come from the base exchange complex. We can prevent the loss of calcium by using sulfate of potash. When the plant removes the potassium, the sulfate ion also adds to the soil acidity, but when it combines with calcium, the resultant calcium sulfate is not very soluble and stays in the soil. This has other good features which will be mentioned later. When we consider the above in terms of natural limestone soil, the story is somewhat different. Up to a few years ago, scientists assumed that limestone soils did not require additional limestone. If we depend on the soil acidity tester, we probably would find the soil to test neutral because small quantities of limestone would be in solution and could affect the soil acidity. Limestone soils will test neutral, particularly during the fall, winter, and spring months, when larger quantities of ammonia and nitrate nitrogen are present. When this ammonia becomes oxidized to nitrate nitrogen, we may get some high acidity readings. However, since most of these soils are tested during the winter months, the need for calcium is easily overlooked. Many of our soils seemingly have sufficient calcium when actually the available calcium is too low for good growth. A number of years ago, I worked with greenhouse soils for Yoder Brothers at Barberton, Ohio. When I first tested the soils, I found the pH reading to be as high as 8.4, in spite of the fact that calcium deficiency symptoms prevailed on the foliage of the plants. The soil also was very compact and became very slippery on the surface when wet, so much so that green algae grew freely on the surface. This usually meant poor drainage and usually means poor aeration. My friends, Dr. Richard Bradfield, formerly at Ohio State University in Columbus, and Dr. Barnes at the Worcester Experiment Station, and I discussed this problem on numerous occasions. It was puzzling. The crops were not producing, and yet the soil test seemed satisfactory. The high pH camouflaged a lack of available calcium. After considerable discussion, the need for a calcium test entered my mind. Dr. Bradfield and Dr. Barnes were skeptical of its value. The problem required more than a test for calcium. It was necessary, first of all, to find out how much calcium was necessary for a given soil, what the saturation point in the soil should be, and how this should be fitted in with our high pH. After several tests and experiments, I decided to pay less attention to the pH test. The potassium and sodium readings on the soil were excessive. I filled a 50-gallon cylinder with the soil, which had a pH of 8.4, and leached it with distilled water. Every day I would add 5 inches of water, collect the amount that came through, and test it for calcium and potassium. At first, the potassium was very high, much higher than the calcium, but as I continued to apply water, the calcium and potassium leached out in equal quantities. The amount of calcium was very low. I applied 35 inches of water in all before the potassium and calcium decreased to the point where the amount equaled that found in an ordinary soil. The pH of the soil dropped to 6.8. Checking back for the past several years on the treatment of the soil, I found that each year a ton of muriate of potash had been applied to an acre of ground for each crop. In the first few years that this had been done, there occurred a good stimulation in field, which prompted the growers to continue the practice. But the practice was continued until it no longer did the plants any good. The cucumber plants began to exhibit mosaic-like symptoms, which became more and more common, as did calcium deficiency symptoms. My interpretation of this was that after the first applications of muriate of potash, calcium was released and stimulated growth. This soil was of acid origin and contained very much organic matter. The colloidal complex included the decomposed organic matter, formed a high base saturation complex, which could absorb large quantities of calcium. The calcium that was absorbed was soon replaced by the added potassium, since the base saturation of calcium was very high. As the practice of applying muriate of potash continued, there was less and less calcium to be released. Finally, it got so low that the soil solution did not have sufficient calcium to antagonize the potassium ions. Then, calcium deficiency symptoms began to show on the plants. The nutrient ions were thrown out of balance and trouble showed up for the grower. I have found this to be a common problem in many areas where the application of lime has been neglected. I immediately brought in several carloads of dolomitic limestone and 1 carload of Youngstown slag and applied it to these soils at a rate of 10 tons per acre. It took a whole crop before the full effect was noticed. A rototiller was used to mix the material with the soil. Root growth was normal. The pH dropped to 5.4 and gradually came back to 6.9. Deficiency symptoms, including mosaic-like symptoms, disappeared from the cucumber and tomato leaves, and the soil became mellow. Drainage was greatly improved. Of course, this was a shotgun method of doing a job, but it meant profits for the growers. The pH was incidental to the problem. As a result of this and other similar experiences, I have depended less and less on the acidity test for determining calcium needs. I feel that agronomists are handicapping their work by placing too much confidence in testing for acidity soils where mixed fertilizers are being used. In many problems that I have worked on, growers have shown me soil reports in which the pH was 6.8. no lime recommended, and yet I applied 4 to 6 tons of limestone because the available calcium was too low. I have increased yields from 50 bushels to 165 bushels by applying sufficient limestone and no additional fertilizer. One of the best cooperators I have came to me for advice in 1952. He had decided after serving in the war years with the Navy to take over 80 acres of land belonging to his father's family to try to make a living for himself and his bride. He secured all the advice he could. According to the pH test, he did not need any lime. He was advised to use 700 pounds of mixed fertilizer an acre to grow corn. He started to farm. Before the war, he had built up a flock of sheep as a 4-H club project. He decided to raise sheep and start another flock. At the end of the 4 years, he was unable to grow over 50 bushels of corn on an acre, and his fertilizer bill was making it impossible to show any profit. When he inquired about this, his advisors told him that his land was submarginal and that if he wanted to grow more, that he would have to buy better land. This seemed like good advice. By accident, he and I got into a discussion of his problem. To me, it was a challenge, and I asked him if he would like to do some experimenting if I could furnish the fertilizer. He agreed to go along. I tested all the fields on the basis of available calcium and found he needed 10 tons of finely ground limestone on every field. The land was rolling and variable in composition. Some was river bottom land. Some contained much clay, silt, and gravel. He did not have enough money to buy limestone for the whole farm. So we decided to take a 16-acre field as a start. Limestone was applied, and the field was planted to corn with 3, 6, and 9 gallons of 7-14-7 fertilizer solution. The field was plowed, disc-harrowed once, and planted. A rotary hoe was used on the corn crop once. Weeds were killed with weed killer. Up to this time, this field had never grown over 40 bushels of corn per acre. On the 16-acre field, the average yield the first year was over 100 bushels per acre. The remainder of the 80 acres in the farm was later given the same treatment, with equally good results. A pH test on such soils does not help very much because of the strong buffer system that exists. It is necessary to determine the degree of base saturation and calculate the amount of calcium needed to do the job. 5 years after I started working with this grower, he won the local 100-bushel corn contest with 143 bushels of corn. The crop was grown with 2 gallons of 10-20-10 fertilizer solution in the row and 2 gallons of the same material sprayed on the foliage 2 weeks before the corn was ready to tassel. I tested a soil for one grower and found the surface soil adequately limed. The grower planted corn, and up to the silking stage, it looked like 100 bushels of corn to the acre. When he picked the crop, he had less than 20 bushels per acre. The ears never did grow. I checked the field again. I noticed that the roots were all in the surface 6 inches. The bottom of the furrow was so hard, it was difficult to get a good sample. When we tried to germinate corn seed in it in the laboratory, we had no success. But when I mixed a teaspoonful of limestone with a coffee can full of soil and planted corn, the germination was above 90%. It seems to me that if we can double the yield of corn in a field by applying 3 to 4 tons of limestone, when we can't get a response to additional fertilizer, the problem involves the chemical and physical condition of the soil, not the amount of fertilizer that we apply. We must keep the horse before the cart. We have been keeping the cart before the horse. Observations at our experimental farm at Olena, Ohio, and observations made by farmers who follow our recommendations convince me that any soil that can be farmed can be productive by applying adequate amounts of pulverized high-calcium limestone. The same may be accomplished with dolomitic limestone, but the amount to apply must be figured on the basis of its calcium content, not on its neutralizing value. Black soils need more limestone. A New Jersey celery grower, Mr. Anderson, discussed his soil fertility problem with me. He grew celery on some of the black bottom land along a tidewater stream in central New Jersey. He said, "I have had an experience with lime on celery that doesn't make sense, and now I want to know whether I'm headed in the right direction." Then he told me his story. 4 years ago, my celery was hardly worth harvesting. I had the soil tested and was told I needed 3 tons of limestone. My celery wasn't improved much. I spent the winter in Florida running a fishing boat. On one of the trips, I happened to talk to a man who did research work on soils in the Department of Agriculture in Washington. When I told him about my soil and what I had done, he told me that I probably needed a lot more lime. Then he added, "If you will send me a sample of soil, I will tell you what I think," which he did. Before Mr. Anderson started back to New Jersey, he received a letter from the man in the Department of Agriculture saying that he would need at least 9 tons of pulverized limestone, and perhaps even more. The grower said he took the letter to the man in the experiment station who had run his first test. When he read it, he said, "My God, you will get your pH so high that you will overlime the soil and hurt your celery." He said, "I couldn't hurt that celery anymore." The grower went on, "I thought this over, and since I could not hurt the celery anymore, I took a chance and put on another 3 tons per acre. That year my celery was better, but not as good as I had grown before. So the third year I put on the third 3-ton application, and you never saw such a crop of celery. The fourth year I figured I had enough limestone, so I didn't put any more on, and my celery wasn't as good. Since then I've been applying a ton every year. I had a pH test run on that soil, and it was not above the neutral point." When he asked me why that was, I told him that we had a lot of limestone soils in the United States that contained 50 to 150 tons of calcium carbonate per acre, where the pH was never above 7.0 because of the limestone. If he had used hydrated lime, which is much more soluble, he probably would have run the pH to 8.6 and had worse trouble with his celery. I told him that I recommended limestone freely, but that I recommended hydrated lime with a great deal of caution. I told him he could get good results with hydrated lime if he used it often and in small quantities. I have applied as much as 40 tons of limestone per acre on some fine black soils, high in organic matter, before achieving maximum yields. During my lifetime, I've been called a lot of names because of my adherence to my ideas of soil fertility. People have called me lime crazy, the man who has limestone running out of his ears, the lime dictator, the lime man who is paid by the lime companies. As long as limestone pays as good dividends as it has for me, I shall continue to recommend it. I do it because the farmer can make money using fertilizer only when he has enough limestone in his soil. I see no reason for spending money for a fertilizer if a farmer can't make money using it. I am convinced that if a farmer uses adequate amounts of lime on his land, he will be rewarded by far greater profits than he can expect from any other practice. I have told many farmers who did not have sufficient funds that they would be far smarter to spend all the money they had for limestone, not for fertilizer, until they were sure limestone was no longer necessary. Then they could expect some big profits using fertilizer. Acid-loving plants and limestone are compatible. Many of our textbooks contain tabulated lists of plants showing lime needs based on the pH requirements or acidity of the soil. In most cases, these lists represent groups of plants which should be grown at pH 4.5 to 5, 5 to 5.5, 5.5 to 6, and 6 to 7. There's only one real interpretation for such data. It shows that some plants will grow at a pH as low as 4.5, and others can be grown only above 5.5, and others must have a pH not lower than 6.5. In other words, it means tolerance to acid conditions or low calcium saturation of the exchange complex. This type of data has given rise to the idea that there are acid-loving plants, that if on a neutral soil you wanted to grow beans, which according to the lists should be grown on a soil having a pH of 5.5, you would have to add sulfur to increase acidity. Then, if after beans you wanted to grow spinach, which requires a neutral pH, you would have to add large quantities of lime. How ridiculous this thinking really is. We know that even though beans will tolerate an acid soil, they will do much better when grown on a neutral soil. The important thing is to get the soil in the proper chemical and physical condition. A good chemical condition means a good physical condition. The azalea gardens of Norfolk, Virginia were having considerable calcium deficiency symptoms on azaleas. They were losing plants every year. The superintendent asked me to help him. We took some of their soil and sick plants to our greenhouse and set up an experiment using 2-gallon glazed pots. Since the soil was very acid, we applied some dolomitic limestone to several of the crocks at the rate of 2, 4, and 8 tons per acre, mixing it thoroughly with the soil, and set the sick plants in all the pots. After several months, we noticed only those with 8 tons of limestone were growing rapidly. Although past experience indicated that these plants should be grown on strongly acid soils. We planted root cuttings and small plants of many different varieties that supposedly required an acid soil in rows across the plots. We had 6 varieties of azaleas and 1 variety of camellias, gardenias, roses, tongue oil trees, blueberries, and others. On plot 1, nothing grew after the first year, partly because the plants made such shallow roots that heat and dry weather killed them. We made no attempt to mulch them. We applied no mulch to any of these plants, even though it was a common practice to do so. Some of them made a little growth, but they all died after the first winter. There is a lesson on mulching here. The general practice is to mulch these plants because they are considered shallow-rooted plants. They need mulch because they practically grow in the mulch. However, on plots 4 to 8, they rooted deep into subsoil and needed no mulch. In 3 years, 1 rooted gardenia, cutting 3 to 4 inches long to be a plant 4 to 6 feet across with beautiful dark green foliage. Azaleas and rhododendrons grew as well on plot 4 as they did on plots 7 and 8. In general, they all grew much better with 2 tons of limestone, but they were not hurt by 16 to 32 tons of magnesium limestone per acre. There was no chlorosis on the foliage of the plants grown on the limestone plots. There was considerable chlorosis on the plants grown on the first 3 plots. Had we used hydrated or burned lime or wood ashes instead of limestone, we probably would have had difficulty keeping the plants alive through the first winter because of chlorosis. When I published these observations in Horticulture magazine, I received a letter from a scientist criticizing my statements and observations. Several years ago, I told my wife to order some pulverized limestone and to apply it freely in preparing a bed where she wanted to set out some chrysanthemums. I warned her not to use hydrated lime, which is the burned form of limestone. I told her to use the limestone liberally, which she did. When I got home that evening, I saw a bag of hydrated lime sitting near the bed. The garden center had sent her the wrong material. I immediately turned water on the bed, hoping to keep the plants from dying. They were all wilted. We saved about half of them, but it took 3 weeks before they showed signs of recovering. That season, they only produced a single stem with a single flower. Even the second year, they did not grow as they should. The next year, they grew beautifully, as did other plants that were set in that year. It took 2 seasons for the harmful effects to wear off. The danger of hydrated lime is its activity. It should be applied the fall before you wish to start a garden. If this practice is followed, the calcium has a chance to become carbonated and also absorbed by the soil colloids, after which it is in equilibrium with the soil. It will no longer interfere with the proper functioning of the roots, nor prevent the absorption of a balanced diet of mineral nutrients. I have had occasion to try out the use of magnesium pulverized limestone on azaleas and gardenias in many landscape plantings, and successfully prevented chlorosis, where most people were trying to correct with iron sprays. In some cases, these plantings appeared to be growing in poorly drained locations. The plants were lifted, limestone was mixed liberally with the soil, and the plants were reset with excellent results. I remember one case where a clump of azaleas was growing on high ground, but the foliage was always chlorotic, as though the drainage was inadequate. We lifted the plants and found they had been set in with sphagnum moss. This was very wet and the roots had made very little growth. We mixed a gallon pail full of limestone with the moss and dug up some soil to give a 1 part moss to 4 parts soil mixture and set the plants back in the same place. It took almost a year before the plants turned dark green to start to grow. They developed into beautiful specimens. There are many other plants included in the acid-loving group with which I have worked, which have responded to limestone treatments. Strawberries have been considered to belong to this group, and yet the best strawberries I have seen grown were on soil where enough pulverized limestone had been added to satisfy the calcium requirement. Blueberries. Definitely acid soil plants, according to authorities, will do much better, according to my experience, on soil where the soil is well treated with magnesium limestone. Mulch is important for blueberries. Gardenias supposedly do best on very acid soils, but I've never experienced this. The most rapid growth, very green color that I have seen was grown on soils to which 8 tons of magnesium limestone has been applied. The amount of limestone needed depends on the type of soil. A sandy soil needs much less than a heavy soil because it has less colloidal clay and chemically active organic matter. I have tried to determine where our ideas on the need for acid soils originated. Acid soils limit the amount of vegetation per square yard. Plants that are tolerant to acid conditions meet less competition on acid soils. I have seen rhododendron growing in mountainous wooded areas with no competition because of the very acid soil. And yet, I have grown beautiful rhododendron on soils that were heavily limed with magnesium limestone. Apparently, because of the tolerance of these plants, we have assumed that they must be grown on acid soil, whereas they will grow much better on limed soil if they don't have to compete with other species. I have seen wild strawberries completely cover acid gravelly knolls. There was no competition. I have transplanted these plants to my garden where the soil was sweet and fertile. They grew well, much larger than in the place where I found them, but they did not produce berries and died out in a year or two because wild clover and perennial weeds crowded them. If they were carefully weeded, they made beautiful plants and grew from year to year, but the berries were sour and fewer per plant. Apparently, too fertile a soil was not suited to their continued existence. They had become adapted to soils of low fertility and acid conditions.
Thanks for listening, everyone, to this episode of The Solution. If you'd like to learn more about the Growers Program or anything you heard in this podcast, visit our website at growersmineral.com. Make sure to subscribe so you don't miss another episode. Thanks. We'll see you guys in the next episode.